Okay, so welcome back to another video. So here we have a little geometry problem, and this is dealing with triangles specifically. And the question asks, does there exist a triangle such that it can be divided into 20/20 congruent triangles? So in other words, if we have just one singular triangle, it could be whatever triangle we want. Is there a way to divide those triangles, divide that triangle into smaller triangles that is congruent to the whole thing, such that we have a total of 20/20 smaller congruent triangles that adds up to, one whole triangle? So there's actually a little lemma that we're just going to prove, and then afterwards, proving that lemma, we will actually use that result to prove the following the following claim over here. So it's really not going to be that challenging, and also more of me just explaining that it is me writing stuff on the board. Of course, there's going to be some diagrams and a little bit of construction that prove the lemma as well, but this is just something just to expect and know what's coming forward. So anyway, let's just jump in. So let's say here we have the following lemma, and here that says that every triangle can be divided into n square congruent triangles that are similar to itself, where n is a positive integer. So here, the way we're going to construct this proof is, let's just take some ordinary triangle. So I'm just going to draw maybe just a little scalene triangle, just so it, like, the triangle, whatever you draw varies, doesn't matter how you draw it itself. Okay, so now I'm just label our vertices, A, B, and C. So this will be triangle A, B, and C. All right. So in order to prove this little lemma, so let's first consider this whole triangle itself, triangle ABC. Now let's actually, so we focus on that line segment AB. Let's draw n-1 points on that line segment, which will then divide the line segment AB into n equal line segments. So I'll maybe just draw, let's see, 3 points. So 1, 2, 3. Okay, so 3 points over here. What I'll do is I'll draw lines that passes through those points, but it's parallel to line segment AC. So that means we'll be drawing line segments that's going in this direction. And I'm sorry if it's not drawn to scale, but don't worry about that. So we draw that, and that means we end up with, so if we drew 3 points, that means we have 4 line segments over here. And then basically you just repeat the process again. So we have line segments here, we draw the points here, then we draw lines that are parallel to AB, and that will help us form new points. So here we have, first we have this point, then the next is here, and then here. And now the next thing is do the same thing again. Now draw a parallel to line CB. So draw a straight line here, and draw a straight line here. Again, sorry, it's not that drawn to scale, so I apologize for that, but you get the picture of how this is supposed to be designed. When you see this, you'll notice is that these line segments divide the triangles into n square congruent triangles that is congruent to the whole triangle itself. So here, for example, I have, so that means we drew 4 line segments, so that would have to imply that there would have to be 16 congruent triangles that is congruent to the whole triangle. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 congruent triangles similar to itself, then it's similar to the entire whole triangle itself. Then hence, we just proved the lemma. All right, so now we can actually move on to the bigger picture and solve our given problem. So now I'm actually going to do a little bit of a calculation. Well, in other words, I'll just skip the step. So here we have 20/20, right? Using some prime factorization, we can write that as 5 times 2 squared, then multiply with 101. Therefore, if you actually perform the right or the correct arithmetic manipulation and all that stuff, what you'll get is you can actually write this down as a sum of squares, specifically 16 squared plus 42 squared. Okay, so we'll just use that to our adjustment. But this is actually really neat because since we're dealing with triangles, 16 squared plus 42 squared in a way is common what you see when you're applying Pythagorean theorem of right triangles. So using this number, we can actually now design a right triangle. We'll just any right triangle we can draw. So I'll say, for example, draw it like this. The way I drew it looks like an equilateral triangle. So let me draw it a little bit more obsolete. Maybe something like this. We have this triangle. So here would be a right angle form over here. We'll call this the same thing A, B, C. Then what I can do is I can actually bisect where angle A is formed down below, and then here we form another right angle over here. And so with the Pythagorean theorem, it's just, you know, those numbers correlate with the basis of our triangle. So over here would be 16 square, or I should say length 16, and then over here is 42. Let me write 16 a little bit bigger. So now the proof follows is that, and I said that it's more just going to be explanations than me writing words down on the board. So just if you can't keep up, sorry about that. This is a new take. If we consider this triangle over here, right triangle ABC, and we have lengths where line segment AB is 16 and line segment AC is 42, and we also have that the angle BAC is a right angle over here, then we applied the following lemma. Every triangle can be divided into n square congruent triangles that are similar to itself, where n is a positive integer. So what we used when we applied this theorem, so we noticed that triangle, triangle, and I forgot to label this point. So where the bisection is, this point right here would be D. So we have triangle ABD. It can be divided into 16 square congruent triangles. I just write CON as a abbreviation, and that such that these 16 square congruent triangles, the smaller triangles, are congruent to I can just write like this as approximate. I write that as similar to triangle ABD. All right, and now apply the same thing for triangle CAD. Right, triangle CAD is can be divided into 42 square congruent triangles, and then such that these triangles are similar to you know, the bigger triangle itself. Well, CAD I'm talking about specifically. And you'll also notice that, pay attention to that, if we can, we also say that, note that triangle ABD is similar to triangle CAD. So that would have to mean that all of the smaller triangles are similar to each other. And another thing to say is that the area ratio of these triangle are, for specifically triangle ABD, then triangle CAD. It follows with the ratio proportion 16 square to 42 square. Okay, and what that implies is that all the small triangles have equal areas, and so equal areas, hence that means it's congruent. Then therefore we can say that we can divide this whole triangle ABC, in other words, into 16 square plus 42 square congruent triangles, hence 20/20 congruent triangles, like so. So yeah, interesting take right over here. So that's pretty cool if you ask me.